What we want to do in this video is get an understanding of how we can approximate the area under a curve. And for the sake of an example, we'll use the curve y is equal to x squared plus 1. And let's think about the area under this curve above the x-axis from x equals -1 to x equals 2. So that would be this area right over here. And there's many ways that I could tackle this. But what I'm going to do is I'm going to break up this interval into 3 equal sections that are really the bases of rectangles. And then we're going to think about the different ways to define the heights of those rectangles. So once again, I'm going to approximate using 3 rectangles of equal width. And then we'll think about the different ways that we can define the heights of the rectangles. So let's first define the height of each rectangle by the value of the function at the midpoint. So we see that right over here. And so let's just make sure that it actually makes sense to us. So if we look at our first rectangle right over here, actually let's just first appreciate we have split up this we've split up the interval from x equals -1 to x equals 2 into 3 equal sections, and then each of them have a width of 1. If we wanted a better approximation, we could do more sections or more rectangles. But let's just see how we would compute this. Well, the width of each of these is 1. The height is based on the value of the function at the midpoint. The midpoint here is -1/2. The midpoint here is 1/2. The midpoint here is 3/2. And so this height is going to be -1/2 squared plus 1. So -1/2 squared is 1/4 plus 1, so that's 5/4. So the height here is 5/4. So you take 5/4 times 1. This area is 5/4. Let me write that down. So if we're doing the midpoint to define the height of each rectangle, this first one has an area of 5/4. Let me do that in a color you can see. 5/4. The second one, same idea. 1/2 squared plus 1 is 5/4 times the width of 1. So 5/4 there. So let me add that. Plus 5/4. And then this third rectangle, what's its height? Well, we're going to take the height at the midpoint. So 3/2 squared is 9/4 plus 1, which is the same thing as 13/4. So it has a height of 13/4 and then a width of 1, so times 1, which would just give us 13/4. So plus 13/4, which would give us 23/4, which is the same thing as 5 3/4. And so this is often known as a midpoint approximation, where we're using the midpoint of each interval to define the height of our rectangle. But this isn't the only way to do it. We could look at the left endpoint or the right endpoint, and we do that in other videos. And if we want to do it just for kicks here, let's just do that really fast. So if we want to look at the left endpoint of our interval, well, here our left endpoint is -1. -1 squared plus 1 is 2. 2 times 1 gives us 2. And then here, the left part of this interval is x equals 0. 0 squared plus 1 is 1. 1 times 1 is 1. And now here, our left endpoint is 1. 1 squared plus 1 is equal to 2 times 1. Our base is equal to 2. So here we have a situation where we take our left endpoints, where it is equal to 2 plus 1 plus 2, or 5. But we could also look at the right endpoints of our intervals. So this first rectangle here, clearly under approximating the area over this first interval, its right endpoint is 0. 0 squared plus 1 is 1. So height of 1, width of 1, has an area of 1. Second rectangle here, it has a height of, we look at our right endpoint, 1 squared plus 1 is 2, times our width of 1, well, that's just going to give us 2. And then here our right endpoint is 2, squared plus 1 is 5, times our width of 1 gives us 5. So in this case, we get, when we look at our right endpoints of our intervals, we get 1 plus 2 plus 5 is equal to 8. And eyeballing this, it looks like we're definitely overcounting more than undercounting. And so this looks like an over approximation. So the whole idea here is just to appreciate how we can compute these approximations using rectangles. And as you can imagine, if we added more rectangles that had skinnier and skinnier bases, but still covered the interval from x equals -1 to x equals 2, we would get better and better approximations of the true area.